Thank you. First, welcome to this session. My name is Epan. I'm here to talk about how we do the stream processing without Lambda in LinkedIn. So a bit of an introduction about myself. I'm a LinkedIn engineer, Apache Senza PMC and committer. Working on this stream processing platform in LinkedIn for about 2 years. Before that, I was in Yahoo and worked on NoSQL database and also the cloud messaging system, which is a hosted pub subsystem. And my co-presenter is Karthik. He's a manager for our streams infrastructure in LinkedIn. Right. So this is the agenda of this talk. So first, we recognize the rise of the stream processing application, and then we talk about some hard problems in the stream processing. Of course, there are many problems there. In this talk, we're going to just focus on the two specific problems. One is the data accuracy. The other is how do we reprocess. Then finally, in the conclusion, we'll summarize our experience and also, hello? Yeah, we'll summarize our experience and the solutions. So let's first talk about the rise of the stream processing applications. There are a few examples that we want to show. First example would be one common example of the stream processing application in LinkedIn is the news feed. People want dynamic news, dynamic content to be presented to them. So how do we do that? Basically, the basic feedback workflow is user integral with our site. Then we track the user activities in LinkedIn. We process it. We get some insight, and also we discover the new content that may be interesting, may be interested by. Then we push out the new content to the user. So all these need to be happening in nearline or real time, so that we increase the engagement. Another example of the stream processing application would be the cyber securities. So pretty similar patterns exist here is user activities like logging or trying the password. Those events will be tracked by the our tracking system in LinkedIn, and then we apply some intelligent model to detect the malicious patterns of the user activities, and then immediately this kind of bad user or malicious user need to be blocked from accessing our sites. So that's another very common example of that. Now, the third example that is, okay, there's the Internet of Things that is becoming the trend. And this actually brings in a lot of use cases for the stream application scenarios as well. One example would be, okay, I wear a iWatch, and then sitting in my car in the morning, in a Monday morning at 8 o'clock. So iWatch reports it's 8 o'clock and I'm not moving, so I'm sitting there. My car sensor will have occupation sensors reporting, okay, now you're in the car, and both tracking information will be sent to the navigation service I subscribe to, and that service will detect, okay, combine those two, okay, he knows, the navigation service will know, okay, you're about to start the car and go to work. So the navigation service now will calculate the route to your work and also push the real-time traffic information together with it. So that's another example that you will just sit there. Now you really need a faster feedback loop that push out the necessary information to the user. So those are all the scenarios that it will become more and more common, and basically it facilitates all the rise of the stream application platforms. Now, okay, we need stream processing platforms to help us to do this like large scale stream processing applications. What are the hard problems? Other problems that in the distributed system also need to be solved here. For example, scalability and the fault tolerance. We're not going to talk about those common problems. We're going to focus on the two specific problems that when doing the stream processing you will actually face it feels like it's hard to or tricky to solve. One is the data accuracy problem. Is reprocessing. So now, what is the data accuracy problem? Often the question comes like, okay, you're doing the data in real time, and the question is, okay, can stream processing generate the accurate result? Are you missing some data there? So the answer we have is yes, but it is not trivial. So in order to help us to better understand what is the problem of the data accuracy, now let's examine a application scenario. So this is a case study for an application scenario that requires the stream processing platform to solve the problem. So this is an ad quality processor application that tracks the ad view events. Basically, that's the events we show to the user, and also tracks the ad click events, which is the user interaction with the ads. Then you can do a join between those two streams and calculate the ad. So the detailed use case is, okay, at 1 o'clock that we show the server, front-end server, push out the ad to the user. And then at the same time, it will mark, okay, that's the 1 p.m. I display this ads to the user, and then that will generate ad view events coming back to be sent to the ad quality processor. Note that here, 1 p.m. is the event time. Basically means when the ads was actually shown to the user, but the time that the ad view event actually arrives at the ad quality processor may be later because of the delivery. So let's define that 1 p.m. is the event time, and then the time that the ad view events arrives the ad quality processor is the system time. We'll view that. We'll refer back to that later. So now the user at 1:01 p.m. the user look at the ads and great, he likes it. So he clicked that, and then it generates another ad click event, be sent back to the ad quality processor again. In this case, now we receive all the events in the ad quality processor, and it runs a logic saying, okay, did ad click event happen within 2 minutes of the ad view? If it happens, okay, great, it's a good ad. Otherwise, it's a bad ad. So that's the simple logic that this processor implements. Now, okay. Now, with this example, let's examine how the data accuracy. Hello? Yeah. Okay. So we know if you examine closer, then it has all the time-sensitive information there, and the data quality issue occurs when you have the event delivered late because of the latency. So this is showing how the latency in the event stream will happen. Overall, this shows how it's a simplified version of how LinkedIn tracking the user activities. So here we show that ad view events and ad click events for the same member usually is coming to the same data center. So it will be captured by the serving layer, sent to Kafka, and then it will be replicated across colo to the other data center 2, and then the ad quality processor in both data centers will set all the events and generate the ad quality report. So here, in healthy case, it's all good. Like the ad quality processor usually sees the ad view events first, and then the ad click events later, and then they can do a timely aggregation of the two events join, and then get the ad quality report. Now, bad things could happen that say the ad click events can no longer be received in data center 1, and then the whole traffic is shifted to a data center 2. Now, it will cost in data center 1, the ad quality event is receiving the ad click event through the cross-colo replication from data center 2 to data center 1 now. And that introduces the latency in between the data centers. So that also allows a opportunity that the add-click events actually arrives later than the time window that the real-time processing is waiting for the events to come. So that is called a late arrival event. Under the same circumstances, we also see there's a possibility of out-of-order arrivals in the data center 2. Because now in data center 2, the add-click events from me will go directly from the local. And the add-view event will still tracked in data center 1 and be mirrored over to data center 2. Now there's introduced another type of problem that, okay, I see E clicked at A in 1:01 p.m., but I didn't see the add-view events. So there's out-of-order streams comes into the data center 2. That's also a problem, like for the data accuracy. If you're too hasty in generating your results, now your result may not be accurate. So those are problems, and how do we deal with it? So a classic solution is Lambda. So the basic like a recipe behind that is, okay, you buffer enough data and sort it based on the then you wait and buffer enough data to address all these late arrivals, order arrivals, and then you sort it when you have the full data set, and then you go process. Then you will have these accurate results. Okay. In LinkedIn, then this is how we implement our Lambda. So the injection layer is Kafka. We track all these events happening from the service tier through Kafka. And then from Kafka, we send it to both the batch processing layer and also the real-time processing layer. In LinkedIn, then we use Senza as the real-time processing, the stream processing platform. It was created in 2013 as an incubator project, and then from last year, it becomes a top-level Apache project. And we've been running it in production for more than 3 years, and it's very performant and a scalable solution for us. Netflix and Uber are also among those, I think, many companies outside LinkedIn who are using this platform in production. Okay, so after we have these results coming from the batch processing layer and real-time processing layer, you need to serve. So in LinkedIn, we basically the result and the analytical result from the processor will be pushed into the serving layer database in the serving layer. So we have two different type of databases here. One is we call it Espresso. That's the a distributed key value store used in LinkedIn for serving the online transactions. And then there's another store, Vault Mode. Vault Mode is also is a online serving store, and it allows the main difference. It allows the bulk load from the batch to push out the whole set of data into it. Okay, great. So this is the Lambda we run, and the question is, okay, does it completely solve the problem? So let's take a further look. So basic assumption here is, okay, batch jobs when they start has full data set, but how about the edges? So let's examine closely to this batch job scheduler. So on the, let's say that on the x-axis, it's a system time that at the 10, 11, 12, 1 p.m., those are the time marks, and we are scheduling our batch job to start at these time marks. Now, the whole arrow with all those small small square boxes that represent the event streams, we actually noticed that on the edge, when the batch job was supposed to start, the full data set may not arrive at the edge yet because of latency in the stream event delivery. So, and also when they're their trend to, okay, I want the analytical result faster, more often, then you reduce the batch size. But if you reduce the batch size, then there are more edges occurring in your whole system. So it is not an easy problem to solve, and to fix that, we actually need to find out what is the safe time that you can start your batch job, and assuming that all the data set is there. So in LinkedIn, that's what we do. We actually need to use an additional system we call Kafka Audit to help make that decision. What does the Kafka Audit do? So Kafka Audit actually will keep track of the number of messages the producers has pumped into a certain topic in a certain time range. So the batch scheduler now has to consult before it starts the batch job, it has to consult the Kafka Audit system saying, okay, hey, this time range, what are the number of messages published in the system? Now, with that, it compares with the number of messages it sees in the batch job and determine, okay, whether it is a safe time to start or not. So it's a additional system that helps us to make the decision so that we can address the edge problem in the Lambda. So this is our observation from all this real practice with the Lambda systems in LinkedIn to address the data accuracy. It is still pretty darn hard with Lambda. Additional systems like the Kafka Audit has to be used to safely determine what is the start time of that. And then there are also like the overhead of duplications in the online-offline systems in terms of development cost, operational overhead, and the maintenance overhead. So especially, well, this whole observation is not regarding to like whether the functional-wise Lambda actually works for us. But the overhead that we are paying here is, okay, additional system to help us in terms of a safe scheduling. Second, maintenance costs, we need to write both MapReduce or Hadoop jobs and the Senza jobs to implement this whole Lambda architecture. And we need to run both offline and online system for that. The maintenance, in terms of like code maintenance, you make a logic change here, you have to replicate the logic change there. So all those overheads that really just make us pay more to get what we get. So naturally, then we are asking a question like, okay, is it possible for us to address this problem in a stream system only? Because anyways, more and more applications want real-time data, so the real-time application has to be there. Then is it possible for us to address that in the stream processing layer only? The answer, this has been an active research area for the past decade, and we actually found out the Google Millwheel or Dataflow guys, the conclusion from their research is pretty convincing. The key concept behind that is, okay, in order for you to be able to address these data accuracy problems in the real-time stream system, you need to handle the late arrivals and also out-of-order arrivals. And now, how do you address that? The key idea is to, okay, introduce a concept of, okay, you will eventually correct the result instead of wait forever for the right result to come. So you first, in the time window that you're getting all the data set for your computation, you first compute the result at the end of the window. And if there's a late arrival or out of order arrival arrives in your system later, now you recompute the result to correct the previous errors. So that's a basic concept that introduced by the Google Millwall guys, and we found it's useful for us. And we'll illustrate that how these ideas will be used to solve the late arrival and out of order arrivals in the following examples. So first of all, let's examine this same use case. Now we at 1 o'clock, at the 1 o'clock we receive this sequence of events, which we get the window open when we receive the 1 o'clock events, and then by the time that we get the 1 or 2, after 2 minutes, the window to create, we get this set of events, then we can compute the window result. Great. But there's a late arrivals from the add-click events. Now, how do we deal with it? We will extend the window size to the late arrivals, and then we'll recompute the window result based on that new window size. That's how the basic concept behind the windowing to deal with the late arrival. Now let's see how we deal with the out-of-order arrivals. So in this case, at 1 o'clock, we receive 2 events from the add-click events. There's nothing from the add-view events yet. So there will be, by the time that we reach the 2 minutes after the window close, there will be now join result in the windowing. We generate that result because that's a time that's the time to emit the real-time result. Now after that, we got 2 events from the add-view events with the event time the 1 and 101. Those are out-of-order arrivals from some other colos. So to address that, we have to extend the window size to the end of these 2 events, and then we recompute the result. So the same concept can be used to solve both the late arrivals and out-of-order arrivals in the 2 scenarios. Now, these requires fundamentally what it requires is, okay, you keep the after you compute the window result, you have to keep the events in your local state, in some state store. And then when the late arrival or out of order arrival happens, you now look back, you look at your store and take the previous window state out and then modify it and re-emit the result. And it requires the state store support that should support high IOs because the event rate comes in is high. So we look at that and we found out Senza is a natural solution for that because in Senza we have a collection of tasks in a job, and each of the tasks will have a local RocksDB store that help the user to save the states in the RocksDB store, and then we group them together in containers, and each container can be launched in a different host. In addition, then local store naturally bring in a question. Okay, what if your node dies? What if your process crashes, and how do you recover? So that is addressed by a changelog topic that we keep in Kafka. Each of the local state mutations that generates a transaction log sent to Kafka, and then when the node crashes, you can launch the same container on another host and read all the transaction logs from the changelog to recover the state. So pretty much that addresses, okay, first of all, the model of horizontal scaling model addresses the scalability problem. The local state help us to achieve the high throughput in the local the state rewrites, and the failure recovery model with the distributed transaction log is helping us to solve the fault tolerant problem. And there are some numbers we got. We actually measured and did a benchmark, and we saw that for each single machine with SSDs, Senza's with the Senza's local RocksDB store, we can achieve the 1.1 million second on a single box. And also the size of the local store collectively from our largest production job is 1.5 terabytes. And that's, those are the numbers make us really happy. Just a note on that throughput that we got. If you store the whole state in a remote store, we tested that the remote store throughput is only like 8,000 transactions per second. So it's way below the local access throughput. Okay. That will conclude my section about our problems and solutions to the data accuracy problem, and I will hand over to Karthik to talk about the reprocessing.
Hello. Yeah. All right. Thanks, Yi. Hi, I'm Karthik. I manage the streams infrastructure at LinkedIn, where we work on stream processing platform with Samza, our pub/sub messaging system with Kafka and change capture technologies. Prior to LinkedIn, I was working in Azure at Microsoft, working on building their messaging stack. All right, so let's dive into reprocessing. So, what is reprocessing? Typically, in a stream processing application, you're always current and you're processing events that are happening at real time. But what we call reprocessing is when you have to go back in time and process events that happened in the past. So we'll take an example to motivate this, and we'll talk about the different types of reprocessing and the challenges therein. All right, so the example that we want to use here is what we call title standardization. So this is very common for you. You walk into LinkedIn, our website, you're editing your profile. It's very common for you to go, let's say, change your title. Like you might maybe be an architect, and maybe you want to go change your title and make it maybe chief technology nerd or something. It's a string. You can put whatever you want in there. We don't really govern that. But at the same time, we do want you to have a good experience, which means that we want your content to be relevant, the ads that we show, the jobs that we show, everything need to still make sense. So in that sense, we still need to know who you are and what your title might be. So that's we have an app for that called Title Standardizer, which works on figuring out who you are. So let's talk about how it is implemented. So whenever you make a change in your LinkedIn profile, in essence, what's happening is you're updating some rows in our key value database Espresso. You already heard about Espresso, so I won't talk about that, but we have another service called Databus, which is our change capture service, which is listening to our Espresso bin logs and is making those updates available for downstream applications to process. Now, in this particular case, our downstream application is our title standardizer is based on Samza. It's getting these events, and it consults a machine learning model, which typically is computed offline in our Hadoop grids, and then makes a best guess estimate as to what your title might be. So, that's kind of the high level picture. One thing to note here is that most of the things that you're going to hear, are going to be applicable regardless of what your input source is. So in this particular case, Samza is processing from Databus. We actually, at LinkedIn, we also have cases where Samza is processing from Kinesis, DynamoDB streams, and such. So a lot of these things are orthogonal to where your events are coming from. So let's talk about the most simple case. It's about dealing with bugs. Every dev is going to write some bugs at some point. It's like gravity. You don't fight it. You just learn to live with it. So when you roll out a bug into production, the first thing, after a few hours, you're going to realize something bad has happened. Hopefully, you're monitoring your system. And at that point, you want to roll back, and so you'll roll back to a previous version of your app, and then you want, depending on your source, you want to roll back a few hours and rewind and replay the events that happened in the last few hours, and that should get you back into the right into the right place. Assuming the processing that you're doing is idempotent, without that, it's going to get harder. So this is the most simple case. Let's consider a more interesting example. So for us, our magic is in our machine learning model, and every day of the week, people are improving that. So every time our machine learning model changes, we want to go reprocess all the 400 million members, right? Because we want to standardize their titles again. Now, that's an interesting problem, because now suddenly it's no longer about rewinding a few hours. It's about going back in time and starting from zero. So luckily, we have a system like Database supports a notion of bootstrapping, whereby we take periodic backups of our member database, and for that matter, every database, and we store it around. And Database supports streaming the events directly from the backups, so that your stream processor can first process them. And then the Database client also makes sure that after you've processed the events from the backup, it can switch over and process events that happened since the backup was taken, and get back online. So it's all done seamlessly in the Database client, which integrates with SAMSA. So this kind of works. The issue is that sometimes reprocessing can take a couple of hours, and if reprocessing is going to take you 8 hours or 10 hours during that time, you are not going to be processing anything that's happening on your live stream and your live updates. So that's not good. So what do? Well, what we do is we run two jobs. So now we have the online job, which is updating, which is basically processing the live profile updates. But we spin up a new SAMSA job, which is going to do the bootstrapping, so to speak. And they both produce results back into Kafka. And that's why, by the way, if you might be wondering why are we not directly writing the results into a database. This is the reason I wanted to illustrate that you want a common funnel where you are putting this data, the output, because once you have two processors producing output, now you need to figure out how to merge it, because you need to make sure that you're only updating the results database based on if the result is happened, you have to basically resolve the conflict based on the last update time, right? So again, this is done by a separate SAMSA job which can do the merge. This can be tricky. In terms of performance, this basically means you might have to read the value for a key and then update it back based on the time. So again, if performance is of essence here, then there are ways to optimize it. What you can do is you can have a RocksDB clone of the database, so that every time you write to the database, you also write to the local RocksDB, and that way all the reads are happening out of the local RocksDB. But regardless, the thing kind of works, but there's still a bunch of caveats. First off, stream processors are pretty fast, so it is very easy for you to DOS the system. So you need to have a bunch of safety guards to protect your live system. So first off, you want to control the max concurrency of your job. You can do that in SAMSA, and I'm sure you can do that in other systems as well, whereby in SAMSA you can control the number of containers, and in the future number of threads per container. Then you also have to worry about quotas. So if you're using, like in this particular case, we built quotas into Kafka in the last year, and and that protects Kafka. We also need quotas in your databases. So Espresso has quotas. Every respectable database out there has quotas. That way you can't DOS the database. Now, even with that, it is still a problem if you are reprocessing a super large data set. For smaller data sets, let's say less than a terabyte, it's one thing. But if you're processing like a 100 terabyte data set, you have to worry about capacity, right? Now in LinkedIn, we have a separate Hadoop grid, which has capacity for doing these kind of ad hoc reprocessing. And this gets more trickier, if you're managing your own data center. If you're on AWS, or Azure, and such, maybe expanding your cluster really quickly is possible. But then again, you have to worry about saturation of your top-of-racks switches, NICs, and such. So at LinkedIn, we care a lot about our site latency. So for us, it is imperative that we kind of separate out our, when we are reprocessing very large data sets. And this is not very common for us, and so this is not something we do all the time. But I just wanted to illustrate that, for those kind of situations, what we have been starting to work on is we've been working on a HDFS system consumer for SAMZA. So with this, the hope is that you should be able to run, in essence, a reprocessing workload in in Hadoop. SAMZA already is based on Yarn, so it already can run on Hadoop. But with the HDFS system consumer, now you can actually do reprocessing in Hadoop. Now this brings us again very close to, in essence, if we squint, it is like Lambda. The only difference here is that we want to avoid duplication of code. So with this, you can take your stream processing job, you can run it in Hadoop by kind of having it configured to read from HDFS. So at least you avoid the duplication of code. Now here, just like in Lambda, you still need to worry about merging. So that's why there's still that step to merge the results. We are also working on another serving store called Venice, and what it aspires to do is to kind of build some of these capabilities into the store itself, whereby you can whereby the store itself will resolve the conflicts coming in from the online flow and the offline flow, and do time-based conflict resolution. So there is no concrete timeline on when this comes out, but this just wanted to kind of explain that that's another set of developments which helps in the area of simplifying this kind of hot and cold path processing. All right, so last point, this is once we have an HDFS system consumer, it makes it much easier also to do experimentation, because many times in this particular case, for example, if a ML model changes, we actually want people to kind of try it out offline, examine the results in HDFS. We already have a HDFS producer in SAMZA. So with that, if everything's looking good, then you want to push it online. All right, so with that, I think we are almost at the end. So conclusion is, yes, it's possible to avoid code duplication, and have a single consistent code path for just achieving accuracy and reprocessing. But yeah, for bigger data sets, some of the problems related to Lambda still linger. We can still avoid code duplication, but you still have to kind of worry about merging results and things like that. All right, so that's pretty much it. Thank you, and we'll be open to Q&A. Thanks. Yes.
How does the ad placement logic work? Like in the beginning, you showed that when you visit the LinkedIn, you see some ad. How does that logic work? It's a real time based on how I'm logging, or it's like something predefined.
Hello? Okay. So I repeat the question. Basically, how does this ad quality logic works, right? So this one is a pretty simplified version. In the real implementation, what we're seeing is basically you will have two streams come in, do a join, stream to stream join, and then do an aggregation. So that is used to generate the click-through rate and the quality and the ranking. So this one is a pretty stripped down, really simple version saying, okay, every 2 minutes you just determine whether you have a click or not, right? So that's happening in real time. Yeah.
The whole time.
Yeah. Can you speak louder?
So I think the question is there any machine learning library for SAMZA? Okay. We at LinkedIn we have some versions of it that we have some teams who have some machine learning libraries which are not yet open sourced. From what we like, I don't know if they have a roadmap for open sourcing that. I know that in the open source there's also a project Samoa. We haven't tried it, but that's supposed to work with SAMSA. So we haven't used it at LinkedIn. I believe they had evaluated it before, kind of building some of these things, at LinkedIn. So.
Just to add to that, Samoa is an open source project. If you log into Samoa webpage, you can see they have actually built the Samoa on top of the mainstream processing frameworks, including Storm, Spark Streaming, and Senza.
Any other questions?
You're from Yahoo, and Yahoo use Storm heavily. Why the LinkedIn use Samza instead of Storm?
Okay. Yeah. So basically, the question is about a comparison between Storm and the Samza, right? So Storm is a okay.
Almost.
Storm is a stream processing for basically it controls the whole workflow. Senza and historically the problem about Storm is always the operational cost, that when you have the bolt stuck somewhere and then the whole backlog happens and then the whole topology gets stuck. There are also some of the state management problem. There's another is a state management problem. The whole state management in Storm is weak. For Samza, the big advantage compared with the Storm are two. One, the operational simplicity, because it is operating on a single, a single job. Like all the tasks are same, so you will only operating on that level. So it simplifies that, and also between jobs, it's the Kafka topic. So you have a nice isolation of the problem. Second, Senza has a local state, which can be highly performant and supports large states. So in terms of for jobs that have for stateful stream processing jobs, then it does brings a lot of benefits.
Yeah, so I would say it's operation simplicity and performance. We have like you shared some of the numbers in terms of performance. We have pretty good results in terms of performance for stateful jobs.